get any more coffee.
Much more coffee.
You are a shocker.
I totally get it. I'm like,
So you're saying I'm trying to date?
Oh. The range. I think we've seen some white. Yes.
So we just did that today. Like we had an orientation meeting today.
The application process, sorry.
The application process was pretty easy.
Where'd John go?
He told us to walk in. Everyone just go where he wanted.
I think he might.
it's just
So like we go to MCCOE's webpage. There's a apply button.
Yeah.
On one page. I kind of feel worried after applying because I never got like a email confirmation to say thanks for your application, whatever. So apply. Might take a couple weeks to hear back though.
Everything is. You have to apply by a certain time frame.
I think for what we did today, I think it's. I don't want to say things.
No,
Like
no.
that. Yeah, we filled the form, but how often are they?
Did you?
Oh, that's right. Yeah, I did.
No.
I did too, but it was like I copied all of my information to like a Google Doc and then pasted it into. So I have everything saved. There's an interview.
Just to see if it will fit, like you'll fit.
Also make sure that your resume is not crap. So you want stuff that you know we're doing go, and if it's make sure your resume is like legit.
Yeah.
So you say you have X amount of years of experience. Okay, do you really? Kind of. Well, I ask about like what projects I've done so far, like things I've done. Yeah, the home lab thing, yeah, it's pretty cool.
Broke a lot of stuff. It's one of the sales that just kept changing until it worked. I was prepared. I was like, get ready. I was ready for some fire back questions. And I was like, oh. Which is pretty, it's better than, it wasn't intimidating. I still was intimidating thinking.
Thinking about it, then actually.
So I was like, oh,
Because they're all pretty cool. Almost there. I will take it.
Yeah.
This is American. She's working.
Yes.
Doing it on Linux. So just FYI, anybody who's on stream Teams can only stream one device to one service. So I'm sharing my screen, which you should be seeing Virtual Machine Manager on Teams. And YouTube is streaming. YouTube is going to be streaming the camera display. So Should be what you expect to see. So I'll go ahead and start. I'm gonna do a little bit of an intro real quick. So the first time we did this, or I did this, I wanted to do a reverse engineering talk. This is more of explore what I've explored. I'm by no means any kind of expert on this, but I take a lot of interest in this topic, and I enjoy a lot of the exploration and trying to figure out how these things work. I am a little bit of a programmer at heart as well, so this goes beyond just normal programming. This has taught me a lot of how software really works at the lowest level. And my goal is to show you a little bit of that. Where?
On
On the stream.
As far as I know, they can.
nobody said anything yet. All right, go.
So I do this so I can see a little bit of the inner workings of software, and then again see how that looks at the lowest level. So the lowest level is going to be machine code or assembly, and I would explore this, and the idea at least is to, or at least what you can get out of this, is I would take this and try to open up any kind of malware. For starters, you're not going to be using this to like debug software, so to speak. If you're going to go into software development, you're going to have your own debugger, things of that nature. The idea here is that once software is compiled, then it is sort of set in stone, and you can't see the source code. So if you could, then it'd be a lot easier, obviously, to figure out what the malware does. But we don't have access to source code. But we can use these tools, some decompilers, some other debuggers that can go into the assembly and look at the raw assembly that the source code was turned into, so to speak. So a compiler, software compiler, would be C compiler, C++, maybe not C#, but a lot of these compilers will take your source code that you write, and it will generate all of the relative instructions down to the CPU, and it generates all of the assembly based on the CPU architecture. So we have, x86, 64-bit, RISC-V, ARM. These are a lot of the different CPU architectures that are out there. And again, once that's compiled, we can't see the source code. But I want to be able to try to go to that lowest level and see and try to at least interpret what the original source code was. So another thing as well, whenever you do write software, I'm not talking about web applications, I'm talking about low level, something you're going to write in C or C++. And whenever you do write these, oftentimes, well, not oftentimes, every time you need to do anything to interact with the hardware, disk I/O, network I/O, display, anything of that nature, you will need to interact with what's called APIs. So Windows, Linux, Mac, they all have their own respective APIs. And malware, any kind of software, it needs to interact with those APIs before it can do anything on a computer. Any disk I/O, creating files, reading files, extracting information, connecting to a C2 server, it needs to go through that API first. So those things in particular are something that I can see inside the binary, inside the executable. So that's one thing I like to look for. But once you need to have the understanding first that any software, any malware has to go through those APIs before it can interact with the operating system. Very, very rarely, I don't even think it's possible. There could be something that, actually, I'm not even going to say that. I don't think it is possible to interact with the operating system without going through those APIs. So that's one thing I'm going to look for a lot of times. And then there's a few other nuances, some ways that malware can hide itself that you could be aware of. And again, this is going to be something to kind of spark your interest. This is something just what I've been exploring. My takeaway of my process, my adventure trying to decompile some of this stuff. So what I've done so far is I'm gonna show off just a few little code snippets, and hopefully at least someone can understand a little bit of C code, or at least understand code in general. But I'm gonna show off some C code, and I've compiled it, and I want to see what that looks like in the assembly. And I've generated some other snippets in here that will show some of the mechanisms that malware might use to hide itself. So this will be a little tricky. I positioned myself so I could see this. So first time I did this, I had a lot of this stuff that I wanted to go over, and I couldn't because I did this. I did a dry run. I didn't do a dry run this time, so we'll see how far I can get. I did a dry run, and I went over this, and like I blew myself away. Like I could not possibly talk about all of this within an hour. So whenever I did this the first time, I dove right in, and I tried to, well, we did a little bit to an extent, tried to reverse engineer WannaCry. People probably know what that is. It's a very famous ransomware that took advantage of a SMB exploit, Eternal Blue. But I jumped right into it, and this presentation is going to be a little bit more of the introduction and what I wanted to go over in the first place. So starting out first, some pretty simple things here. First, I'll print, then I'm going to set some variables, x, y. Well, that's fine. I can call it anyway. Set some basic variables. I think we can figure out what's gonna happen here. All I'm gonna do is add. I'll subtract, multiply, divide without any remainder, and I'm gonna print these. So first thing to keep in mind, again, anytime I call anything on the operating system, it's including like these print. This is an API. This is built into the operating system to allow me to do this and print these things to the console. Okay, this isn't something I write in the code. I'm using built-in functionality within Windows. So if I go here and two tools I like to use. One of them is going to be x64 debug, and the other one will be Binary Ninja. So within x64, there's a few things to keep in mind with these debuggers. x64 will actually launch the code and then stop whenever it enters the first instruction. Binary Ninja and Ghidra, for example, they will go through a decompilation process. So whenever I run this in, I thought audio was working here.
On Teams.
That's weird. I'm getting audio from here. What about now? No, it's definitely not working. How about now? All right, well. Thought it was. There.
Oh, there you go.
It's working now. Okay. But keep that in mind. And some shortcuts I can do. Also, whenever I'm in here, I got these shortcuts, so I usually use these a lot. And whenever I'm in here, if I hit run, okay, it's going to execute this code until either I hit a breakpoint or there are certain built-in breakpoints within x64. So one of them is going to be the address point of entry. So this is within any binary that you compile. Again, a binary is going to be an executable or an ELF or whatever the Mac binary is. It's compiled code. So this is stopping at this point of entry. And at some point, I believe it's going to reach this. No. Where is this? So here's one of the things I have to do sometimes. And I will use Binary Ninja to get an overview in what Binary Ninja will do is show me its best guess at showing me what the source code looks like. So Binary Ninja and Ghidra will go through and run through the code and give me a best guess of what it thinks the source code was, and the respective functions as well. And within this, I can see all of the raw assembly that this compiler generated for this code. So one of the things I like to do, whenever I'm going to learn this, is I can run this, and each of these instructions, each of these lines goes step by step. And I can go through here and see exactly how this interacts and how the CPU and how the memory, how the registers will operate. So one of the things we see here, one thing I will explain are registers. So in the world of CPUs, in the world of computing, CPUs have a certain area built onto them. You either have RAM, and then you have these registers. So these registers are used to hold memory addresses that can be used to go pull data out of RAM, essentially. So this is all a standard for our different CPU architectures. So x86 and 64-bit, they will use these respective EAX, EDX, RCX, RAX. 64-bit has a lot more different types of registers, but they are still largely the same. They're the same function. So one thing we see here is, for instance, this instruction. So we'll say moved, which is basically copy or set. And it's going to move into RCX the address of this string, hello world. And then anytime you see a call, that's going to be a function that's going to get called and executed within this code. So printf, whenever this does get called, it's going to go into some other built-in stuff with the operating system, and it's going to print what I have in RCX to the console. And forgive me, I'm going to try and find this real quick. in x64. Actually, let's do this. I'm gonna go backwards for just 1 second. One thing I'm gonna do in any kind of debugging is look for strings. So strings will be something that will be hard-coded, usually, if you're lucky, in a binary. And it could be hard-coded information. It could be some metadata. It could be stuff that gets printed. It could be some configuration. And at the very least, it could lend us some clues as to what this binary is doing. So within x64, I can go search for all modules, string references. And this is largely all useless for the most part. But things you might see in here, again, might be passwords, might be IP addresses. But I know this prints hello world. And I can see a lot of the same things in here. So we saw this on Binary Ninja. It moves the address location of this string into the register. And again, registers, they are there to store addresses for information. The register is a link or an address of something stored on, for something stored on a RAM. Oh, I've already got a breakpoint set there. That's right. Okay. So another shortcut, I can hit F2 and I set a breakpoint. So breakpoints in software, any kind of debugging, will be, as this code executes, I want to stop on that instruction. I want to stop right there, and I want to see, and especially in this, I'm going to see what is in memory, what has been loaded, what's being done, what's in registers, what's down here in memory. This looks like crap, but this is actual raw data that's sitting on the memory in this binary right now. So I can execute this safely. I know what's going to happen. It's going to stop right there. And then another two things I will do is step over and step into. So step over is going to execute the instruction right here. LEA is load effective address. It's loading the address of that location, this data segment, into RAX. Step over is just going to execute that and be done with it. Now, I'm not going to go into the print, but whenever I hit step into, if it's a call, such as this, to call this function, it's going to go inside that function and I can see what's in that next function. If I step over this, so right now my instruction pointer is sitting on that. I step over this, okay, it's going to do it. And I'll also see on the console I have my print. So I know that is the printf function. It's not plainly obvious, but I do know, and I can also go back here and again use this. This is the pseudo C. This is what Binary Ninja thinks this looks like, and see that it's going to call printf and go through that. So moving on, I can still go down and I'll step through these. Now, before I execute this, This is a simple thing. It's going to add EAX and EDX. So over here, I have RAX, and I know they're not EAX and EDX, but that should be 50, 59, and 43. So anytime you look at data in here, obviously those aren't the two integers that I created in my source code, right? But that's hexadecimal. So if that's 59, right? On the top.
Mhm.
If I were to, see if I still have this. Yeah. No. If I do 0x59, okay, that's going to be 0. That's 80401, and 9 is going to be 8 and 1. So if I, that's my binary for that hexadecimal. If I were to add that up, okay, it's going to be whatever I had in here, 63. It should be. Or, sorry, 67. And then once I call this, once I go through that, it's going to add those two, and I believe it will give me the result back in RAX, which is 9C up there, right? I can see. And that's going to be my total. And then this is just going through a few little things to set up the print function again, and it's going to print it. I can see, then we'll do sub. And again, I'll print it. Then, real quick, on division, division will not give, if I'm dividing something and it's not even an even division, there will be a remainder. That remainder will get stored in a different register. I don't know exactly what it is right now. I want to move on pretty quickly, but the big thing I'm displaying here is that you can go through these instructions one by one, and one of the things I'm going to do in any kind of analysis is see what is sitting in these registers and see what is sitting in the dump. So there's that. Another, we might go back on that. Another way that malware will hide itself is to do this thing called, it's this thing called TLS. It's in here. And it is thread local storage. I believe it is only a Windows thing. But anytime Windows creates a process, anytime Windows creates a thread within the software, it will call this stuff. It will call this function that I can create myself. So this is a function that I've created myself. And what you can do here is that some debuggers might not go through this and recognize this, and it will just happily execute this in the background without stopping or really giving any kind of indicator that it went through this, that it did this. So one of the things that malware will do is put stuff in this TLS callback that you can see here. I'm going to call this function I have terminate if debugged. Okay, we can probably figure out from that what's going to happen. If this executable is being debugged, this process is going to terminate. It's going to kill itself because malware doesn't want to be reverse engineered. And this is something that Windows will set whenever you execute this, and Windows knows if software is being debugged, and it will set these flags in here. And again, this is a built-in function within Windows, and if it's detected, then it's going to stop. That's going to kill. So this is something to be aware of and look out for in malware. So I have not necessarily been able to, I'm not the best at finding this in Binary Ninja, but I do know that x64 gives me the ability to see these better. So within x64, I can go pull up my thing, and I have preferences here. Oh, I don't have it checked. And I will tell it to break on these TLS callbacks. I don't want to trust just user TLS callbacks, but it should work. I'm going to use user and system. So whenever I call these, now I believe it is sitting at TLS callback 1. No, let's try one more. Okay. So if you guys remember the strings that I put in here that said thread attached, this is what's going on here. And somewhere in here, I think if I go here, this one. Nope. Here it is. So this is going to call the built-in is debugger present. And one of the things we're going to do here is execute that. And within assembly, we will set these flags, we will set these registers to different values, and then this test will compare those and then set either 1 or 0 based on the outcome. And then also, this JE will jump if equal, I think. I'm not exactly sure, but it will jump. And this jump is actually going to go through and return and tell us something's wrong. Or, I'm sorry. Right now, this isn't going to jump because I know the debugger is present. And I can see here, it's going to get past that, and then it's going to execute all of this, and then it's going to call the exit process. I don't want that to happen. So one of the things I can do to get around this I'm going to set a breakpoint on that. And one of the things you can do in a binary is I can actually reverse this. Set that to 7. No, I did this in. Okay, you know what? Let's just do this. So before test EAX works, I believe that is 1 over there, right? Check this out. Okay, I tested that, it's not gonna equal. And now I know my red line here says I'm gonna pass over this function, all of this functionality right here. And it's gonna execute and continue on as though there was not a debugger. So I can patch that. I can save that back to the binary and get around that stuff as well, so that I don't have to go through this process again. I haven't done that in x64, so I can't show that, but I can, what I would do is change this to be, I forget, I don't know exactly what the code is, but I can change this to where it would not jump or jump down here so that I can get around this debugger stuff. But again, that's a built-in function on the operating system to detect that. I can change that in this binary as well, and I can affect that stuff. I can set breakpoints, and I can, like I said, like I just did, I can change EAX and affect the entire operation of this binary. So real quick, EAX and RAX, I know I'm saying EAX, but you're looking at RAX. The R versions of these registers are the 64-bit versions. The E versions, I guess you could say, are 32-bit versions. So that's another thing, cool thing I can do. Another thing we have, is to obfuscate code. So full disclosure, this is not a lesson on writing C code. I asked GPT to write this stuff. I'm not an expert in writing C. My goal is to demonstrate how this works. So the functionality I have here, I wrote some stuff to get the code, get the assembly code from this function and print the respective hexadecimal code. And then I can copy and paste that hex code into a char array, such as this. But I also have that over here. So this is raw binary essentially. This is hexadecimal code, and this represents the assembly code that would get executed. But what I can also do is this is just some simple XOR encryption as well. I've gone through and I've iterated through this, and I've XOR'd that on just a simple code, a simple character, and I believe it will reverse that and load this into memory. So here's another tidbit, here's another helpful hint as well. This virtual allocation, I would assume, is another built-in Windows thing that will take my code, put it into memory, or no, actually, sorry, this one is to give me a section of memory that I can execute code in. So whenever a binary is loaded, everything's static, everything's in place, but I can still call this and get additional memory to execute my code. So a very important thing, a key thing you're going to look for in any kind of malware analysis. Because whenever that's happening, chances are there's some tomfoolery going on. And something is being executed dynamically that was not in this originally. So then I get that allocation, I will copy my code into it that I just XOR'd, and then I can call that, it's going to go into there, and it's going to print my flag that you saw previously just a second ago. So that is this one. Oh, work. How to get into that? So again, I'll go to my main, and you can see my stuff here. And that's just a bunch of garbage. It is XOR, it is XOR encrypted, but I can't make anything out of that. I could, I can go through and I can recognize and say that I see my XOR right here, this little caret symbol. I can go through and I can copy and paste that and put it in Python, or put it, get it outside of this binary and try to interpret it then. But one of the fun things I can do with this is I will set a breakpoint as soon as that is copied into memory. And then I can see what the original code here was. So I believe this should be. So I can actually debug in Binary Ninja as well. It tells me and says, yes, I know what I'm doing. Largely, that's the same. Why will you not run that? Let's go here. Start. See that message? This may harm your machine. I don't know. Usually. one of the reasons I like using X64 over this for debugging, because it's a whole lot quicker as well. So one thing here, I know you can see it here. This is my unencrypted code. Now I should be able to go back before this gets allocated, and I cannot. I won't be able to see that. Let's go. No. Start. Let's see, this is okay. Line by line. Oh, you know what that is? Actually, that's because I still have that function decoded. That's fine. Well, I didn't do that very well. But again, malware will use this API function a lot to dump executable code and jump to that. And the whole premise of that is to make it not so easy to statically debug and analyze. I cannot, there's no way I can figure out what that is, what all this does, without actually running this or trying to extract this somehow and see what it looks like in memory. I'm gonna do one thing quick. Let's back up. All right, here's another thing I can do. And real quick, these are all of the libraries. These are all of the DLLs that will get imported into a binary whenever you open this up. And one of the things I can do in here is go look for these respective function calls, these respective API calls, and set a breakpoint on those. So this is another thing I like about X64 is that I can set these breakpoints before these things get called. So think about any function that malware might need to use to interact with the operating system. File creation, writing a file, reading a file, calling a socket connect, or HTTP request, memory operations, service operations. All of those will go through here, and I can set a breakpoint right here. Set, no, okay, let's see. And if you're unsure about any of these, I can also go to Microsoft. I can go to Google and look up every single one of these APIs and see how it's set up, how the parameters are fed to it before it gets called. But I have that there. Let's do this one just for the fun of it too. And I'm going to see here, I'm going to find out where this got called. if anyone's ever programmed before, you might also know what a stack trace is. I see I'm sitting right here. This is my breakpoint. This is what has led me to that. And well, there's my string I saw, my printf pointer and function. And this one, no, that's not just yet. Well, let's go see where this goes. No, I think that is it. That should be it. Overall, here. That's my other breakpoint. I've already got breakpoints set. Okay, so this is going to be calling my function that I just set in there. Is that all right over there? I'm on my cursor. Yeah. This is my newly created function that I dumped in there. And this is going to show this at some point. Well, if I go in here, F7 to step into. I know you see that printf and function, but this one, I believe, just loaded that string into the registry, the address of that, and it's going to print that. Now I can show you in here, I think, this stuff will not exist so this right here, these are my breakpoints. This is what I just set a second ago inside that deobfuscated function. That doesn't exist yet. Now it should. Okay, I think it's getting put somewhere different each time. Interesting. Okay, but anyway, wanted to show you what that would look like. So those are a lot of the some of the things that I've seen and I've read about at the very least, and try to show you what that looks like in the source code, and then what that would look like in the analysis as well. A few other tools I like to use real quick. PE Bear is going to be a really good one. This is a really good tool to open up an executable and look at the insides of it. Give us a lot of information about this. I think this was some kind of virus. I think somewhere in here, there might be some IP addresses, but PE Bear and then DIE, detected easy, is another one that would lend a lot of information to looking into Windows executables. So I don't have a whole lot of time, but I know it's still like just presented everything as through a fire hose. And I still don't have enough time to go over another thing I wanted to. So, any questions?
Not so much a question. I think it's fascinating. Some of the debug tools are breaking down an exe and looking at source code or compiled code and being able to look at code you shouldn't. Especially if, say, you have a back app developer and they can put passwords and endpoints in there that are unencrypted. I think that's if you're doing like app development yourself, being able to go back and review your own stuff.
You can
make sure
encrypt it
it's
inside
not-
the binaries and run through a function that would decrypt that before it gets thrown into memory or used. If that's what you're asking.
And it's super fascinating.
Okay. Well, we gotta get out of here, so I appreciate you guys. I will- Uh, I don't understand the question. Oh. GDB is a little bit more of an interactive debugger. There's gonna be differences between static and dynamic analysis. GDB is usually used on Linux. It just depends on if you want to use CLI or a GUI or something in Windows or Linux. Alrighty. Thanks, everyone. We'll have, I'm sure there will be some more to come from me in the future. I still have a lot of other stuff I'd like to go over. Thanks a lot, Brandon.
Thank you.
Thank you.